A couple months ago, NVidia released a new type of generative adversarial networks called StyleGAN. These produce state-of-the-art, beautiful-looking images of human faces. Now there's a couple new things that StyleGAN brought along with it, and we're going to be going through in a series of videos exactly how to implement all of these new changes that StyleGAN brought for us. The most important one, and the first one that they introduced, is called Adaptive Instance Normalization. Adaptive Instance Normalization is a method of applying the latent vector to each block in a generator. How it does this I will explain later. So we are going to be implementing this part of StyleGAN in order to generate pictures of Pokémon today. So to start off, we have 10,000 images of Pokémon, and as you can see, here's a couple of examples, cute little Pokémon, and we can move on now to talking about how we're going to generate these with Adaptive Instance Normalization. First, we will want to implement our gradient penalty. I'm not going to explain gradient penalty as I did it in the last video, so if you want to check out what it is, why it's important, and what it does for us, go and check out that video first, and then come back to this one to finish watching about Adaptive Instance Normalization. Next, I'd like to explain what Adaptive Instance Normalization might look like, or just adaptive normalization itself. So we will start off with some data, and on this graph I'm going to be going through exactly how to normalize and then adapt that data. So here we'll start off with our blue data. This is just some random data that I made, generated, whatever. It can be anything. And in our case, it's going to be our image representation data. So what we can first do is normalize our data. To normalize the data, we want to subtract the mean of that data from it and then divide it by its own standard deviation. So this means that after normalizing the data, it will have a mean of 0, an average of 0, and a standard deviation of 1. So this normalized data you can see as the orange bars here. Then we will want to adapt this data. So now we can give it a new standard deviation and a new mean. So here we have a scale and bias parameter. First we will multiply by the scale. So that is going to be 4.1 here. So it'll make it a little bit larger. And then we will bias it. So it's minus 13. So that's going to move it negative 13. So now we still have the same content. We still have the same structure. But now our data has changed so that we can do something different with it. So the way that this works in Adaptive Instance Normalization is that we adapt each channel of an image individually. So first we'll want to get our image representation and two different parameters, our scale and our bias. And these scale and bias will have as many numbers as we do filters here, so that we can scale and bias each layer individually, each channel individually. So we will start off by getting our mean and standard deviation of the image representation for each channel, and then we will want to subtract the mean in each channel and divide by the standard deviation in each channel. So now each channel has been normalized based on its own values. Next, we will want to reshape our scale and bias parameters. This part isn't too important. And then we will want to multiply our image representation, each of the channels, by the scale and bias parameters given to us from our latent vector. So as an input, we have three different parameters here, three different inputs here. Our image representation, our scale for each of the channels, and our bias for each of the channels. So this is how our latent vector is going to affect each and every block of the image, because it can take in an entire image and change the style at that particular block, which can then change the features when it actually comes to a full image. So now let's talk about each generator block. So last episode, I simplified this by just making each generator block into its own function, instead of actually having fully written out each time we have a generator block. So first what we'll do is we'll want to get our gamma and beta parameters, and this comes directly from the latent vector. Our gamma and beta are going to be the parameters. Gamma is going to be the scale, and beta is going to be the bias. So now we'll want to use our regular stuff for the actual generator block. We will upsample, we will use convolution to get and extract features, and now we'll want to use Adaptive Instance Normalization. So now we will normalize each of these features that we've extracted, and then we will want to scale and bias based on our latent vector. So now if we want more snow, we can get more snow. If we want a nose or more noses or something like that, we can get that at each individual layer and for each individual feature. And then we will, of course, get our activation of ReLU, and we will let it go for the next generator block. Next, we'll want to move on to the architecture of our generator. Now, we want to add a latent mapping network. This is a network of fully connected layers to change the latent input into a new latent vector. The reason why we want to do this is because the features in our latent vector want to correspond to the features in each of the channels. But a latent input is completely random. So one value might be for, say, snow, and the other one might be for cactuses. And so these two can be contradictory. If you have snow and cactuses in the same image, that wouldn't exactly make any sense. So now we have a mapping network which can kind of disentangle and kind of make sense of this input, of this latent input, so that none of these contradictions actually happen. So now we'll want to grab our latent input, reshape it to be a small image representation, and then use our generator blocks to apply both the image representation and the latent vector, the mapped latent vector. By doing this, we are now affecting each generator block with the latent vector, and we'll see exactly what that can do for us in future episodes. But for now, let's just say it allows to be disentangled and improves the quality of our images. So other than that, our generator is exactly the same with the same inputs and the same outputs. Our discriminator now exactly the same with the same inputs and same outputs as last time. And so since all of our models have the same inputs and outputs, making the compiled models, the training configurations is going to be the same as well. So we can have our discriminator training, our generator training, and those can both be very simple, as well as the training loop. And now I've been training this for a little while already because I wanted to make sure that we could train for a long time and get some good quality images. And so now we're looking at the same training loop as we had before, as we still have the same inputs and outputs as we had before. So nothing new is here, so I will get back to you guys once this is finished training. I'll see you guys then. So now that our iterations have finished, we can take a look at what exactly our generator has done. So looking at these images, it looks like it's done a pretty good job of collecting, the general shape and features of a Pokemon. It's excluding things such as eyes or legs or things that might be a little more difficult to generate, but it's generating pretty well what Pokemon should be. Now we can move on to our loss values throughout training. It looks like the discriminator started winning again, but just by a little bit throughout our iterations. And looking at this, we can see our gradient penalty loss value. We can see again, it spiked up at the beginning as they were kind of initializing themselves in the right place, and then slowly, kind of rose up again after that. So today we went through Adaptive Instance Normalization. We saw exactly what it does, how it works, and we generated some images using it. This is the first of 5 or 6 parts that we're going to be implementing StyleGAN with. And if you enjoyed, leave a like, and I will see you guys on the next episode of Matchue GANs. Have a good day.